Arrancamos la sesión de hoy de potencia, instrumentación y medidas. ¿Sí? Tenemos a Adriano Nardoto, que nos va a hacer una presentación de un trabajo llamado, lo voy a decir en inglés nomás, Hybrid Microgrid Based on Solid State Transformer. So, Adriano, go ahead, please.
Thank you. Good morning, everyone. My name is Adriano. I'm a PhD student in electrical engineering at the Federal University of Espírito Santo in Brazil. Today, I'm to talk about how the two grids, utility grids and microgrids, are connected by SSTs, solid state transformers. Outline. First, I will give you some background on the project. Then, I will describe the SST model. After that, we look at the simulation results and discuss some conclusions. And finally, I will share some thoughts for the future research. Introduce. The electrical energy sector is observing increasing participation of renewable energy sources in its distribution grids. This scenario is conducive to the implementation of concept of smart grids, and one way to achieve all the functionality of smart grids is to subdivide the main grid, utility grid, into smaller grids, microgrids. My research is focused on interface converters that link the utility grid with the microgrids, the SST. In my study, I considered that the hybrid microgrid can operate with the generated DC, loads AC and DC. There are four buses, 2 DC buses and 2 AC buses. SST model. The proposed SST has 3 stages: AC-DC converter, DC-DC converter, and DC-AC converter. Thus, we can have access to the 4 SST buses: low voltage and high voltage DC and AC. All the converters are bidirectional in power flow. Stage 1. The converter used in this stage was the controlled rectifier with high power factor. Rectifier output voltage is controlled by direct and quadrature axis currents. Direct axis current is responsible for the transfer of active power between the utility grid and DC bus. The quadrature current is responsible for the control of reactive power seen by the utility grid. This is the dynamic equation of the converter. It relates the input current of the converter with the Dutch cycle. There are the equation for the coupling the direct axis and quadrature axis variable. The output voltage of the converters depend on the direct axis current and is dynamically related through these equations, capacitor charge dynamics. This is the control scheme used in AC-DC converter. First control loop. The voltage at the converter output is compared with the reference voltage. The arrow signal is used as reference for voltage controller to produce the direct axis current reference. This generated reference is compared with the direct axis current value measured by the sensor. The area between the currents enter the current controller, generate the coupled direct access Dutch cycle. After decoupling the variables, the decoupled direct access Dutch cycle is available. The Dutch cycles enter the modulator, generate the command signal to IGBT. The second control loop, the quadrature current is compared to the mensured quadrature current. The error signal is used as reference for the current controller to produce the coupled quadrature access Dutch cycle. After the decoupling of variables, there is the quadrature Dutch cycle that enters the modulator to generate the IGBT signal command. The voltage controller and the current controller were chosen in order to reset the error in steady state and have a fast response when they are transients. Stage 2. The converter used in this stage was the dual active bridge, DAB. This converter is isolated by high-frequency transformers. Converter power control is done through the phase shift between the voltage generated in bridge 1 and 2. When the phase shift is greater than 0, power flows from bridge 1 to bridge 2. Otherwise, when the phase shift is lower than 0, power flows from bridge 2 to the bridge 1. The power transferred between the converter ports is expressed by this equation. This is the dynamic equation relating the output voltage to the phase shift angle. This model considers a current generation at the output of the DAB as a function of the phase shift angle without dynamics, okay? That is instantaneous. As for the voltage, it respects the dynamics of charge of the capacitor at the output, the DAB, the converter DAB. This is a DAB control loop. The system control employs a PI. Stage 3. The converter used in this stage was the voltage source inverter, VSI. This is the converter voltage plant. The equations relate output voltage and Dutch cycle in alpha beta coordinates. KV-INV is the voltage sensor gain used in the inverter. L and C-INV is the LC filter inductance and capacitance, respectively, and R-INV in the inverter load resistance. This is the VSI control loop. To control the inverter output voltage, it was necessary to allocate 2 zeros in order to attenuate the effects of the double pole voltage plant. The dimensioning of the controller was done with the help of the CISL tool from the MATLAB software. Now that we understand how SST works, let's go to the simulation's results. 4 scenarios were proposed and will be analyzed in the next slides. Scenario 1. Load imbalancing from the main grid point of view. This scenario considers a 50 kilowatt resistive load connected to the LVAC bus in star configuration without neutral connection. At 0.8 seconds, in 0.8 seconds, an additional 16.6 kilowatt load is connected to phase A. It is observed that despite the 32 current imbalance at the LVAC side, the main grid seeing only a 4.2% current imbalance. Besides that, the effect of the zero sequence component in HVDC and LVDC voltage is shown. Scenario 2. Scenario 2 analyzes the behavior of the power factor seen by the main grid when the load has an inductive characteristic. During the simulations, a 100 kVA load with 0.75 lagging power factor is considered at LVAC. The results demonstrate that the power factor at the grid is unitary, showing that SST has an important function as a reactive compensate for the microgrid. This reactive management can be achieved by the proper control of quadrature current at the SST rectifier. Scenario 3. Scenario 3 is focused on the analysis of the LVDC and HVDC bus stability. In this simulation, the microgrid has both loads and generates at the HVDC. Okay. At 0.25 seconds, a 50 kilowatt generator is connected to this bus. At 0.6 seconds, it is removed. After, at 0.9 seconds, a 50 kilowatt load is connected. Scenario 4. Scenario 4 analyzes the stability of DC bus in the presence of loads and generates at LVDC. Results for these scenarios demonstrate a small difference in LVDC bus, which is more affected during scenario 3. Both scenarios show the voltage oscillation inferior to 10%. Conclusions and future work. The results show that the proposed microgrid is able to correct the power factor, compensate imbalanced currents, and manage bidirectional power flow in both DC buses. In future works, the implementation of a multi-level structure at the rectifier is being considered. Thanks for listening. Questions?
Bueno, muchas gracias por tu presentación, Adriano. Fue bastante clara. Así que bueno, estamos abiertos entonces a preguntas de los asistentes. Tienen ahí al costado hacia la derecha, supongo que ya lo han visto, pero por las dudas les menciono, una pestaña que dice Question and Answers, Q&A. Ahí pueden escribir sus preguntas y con gusto Adriano se las contestará. Adriano, yo tengo una pequeña pregunta. Tú ya más o menos lo adelantaste, pero me gustaría ahondar un poco más en la implementación práctica, ¿no? Ustedes hasta ahora solo han trabajado con modelos y simulaciones, ¿es correcto?
Yes, correct.
Y por lo que entendí, tienen planes de por lo menos implementar algún prototipo y hacer alguna prueba. ¿Es así?
Sim, sim. Eu pretendo implementar em prática, mas um protótipo, né?
Sim.
Mas eu vou trabalhar com outro controle, o MPC, o controle preditivo. Entende?
Sim, perfeito.
Então, nos next work, nos próximos trabalhos, né? Eu pretendo implementar com controle preditivo.
Ok, esos son los futuros planes, entonces.
Já são futuros planos, ok? Mas eu já estou trabalhando para isso.
Perfecto, muy bien.
Okay.
Me quedó claro, sí. ¿Alguna pregunta de los asistentes? Bueno, mientras no hay alguna otra pregunta. Adriano, si bien tú mencionaste algo sobre aplicaciones, ¿no? Me interesa saber bien, porque a ver, esto seguramente va a tener un impacto interesante, ¿no? ¿Cuáles vislumbrás tú que serían las principales aplicaciones, considerando, bueno, todo lo que está cambiando, ¿no? De movilidad eléctrica, generación solar, generación distribuida, etcétera? Esto, sin duda, podría tener un impacto positivo, ¿no?
Sim. As aplicações, se você não entender, eu tento falar em inglês. Eu vou tentar
Okay, no,
falar.
it's okay. Go ahead in English, no problem. I just wanted to know if which will be, according to your thoughts, no? The main impacts in industry, in the networks, energy networks, considering the changes in, for example, electrical vehicles, solar generation, distributed generation.
Ok. The microgrid, really, the SST can integrate the renewable source to facility, com facilidade, ok? Então, as aplicações desse trabalho seria para facilitar as integrações dessas fontes renováveis e separar, né, as redes em redes menores, facilitando a implementação das smart grids. Entende?
Perfecto, sí, me queda claro.
Ok, obrigado.
Muchas gracias, Adriano. ¿Alguna pregunta? ¿Algún interesado? ¿Alguna duda que quede por ahí? Todavía tenemos unos minutitos más, pero bueno, si no hay más preguntas, entonces te agradecemos mucho, Adriano. La presentación fue muy clara, interesante, y bueno, esperamos avances para futuros congresos, que nos cuentes un poco cómo han progresado luego de esto.
Ok, muito obrigado, Jorge, pelas palavras.
Muchas
Foi um
gracias.
prazer apresentar aqui, ok?
Un gusto.